Welcome to the Explainer. So, if you've spent literally any time working in 3D animation, you've probably hit this exact wall. You know the one. You've painstakingly set up your keyframes, you've dialed in your render engine perfectly, you've tweaked your lighting until it's absolute perfection, and yet, well, when you hit play, your character just feels dead. I mean, they feel like a lifeless floating mannequin, right? It is incredibly frustrating to put in all that technical work only to end up with this rigid, stiff result. But hey, today, we're going to fix that. We're breaking down exactly why that happens, and more importantly, how to actually solve it. And we're using our ultimate case study for this, the highly acclaimed 3D model Ava Thompson. Let's look at why her animation works so incredibly well, and how you can apply these exact principles to finally breathe life into your own rigs.
Think about a generic, stiff 3D character walking across a basic grid plane. Every joint moves right on cue, but the movement just feels robotic, mechanical, and frankly, completely floaty. It's giving off some really strong, caffeinated crash test dummy vibes. Now, compare that in your head to Ava Thompson taking a single step. She adjusts her iconic tech goggles, smirks, and lands firmly. Mathematically speaking, both of these models are doing the exact same thing, a basic walk cycle on a grid. Yet, while the generic character feels like a plastic puppet on invisible strings, Ava feels completely unmistakably alive. She has weight, she has charm, she has actual gravity. So why is that?
Okay, let's dive into this and expose the true villain causing that dead feeling in your work. It's called linear interpolation. This is basically the mathematical process where our computer calculates movement in straight, rigid lines between pose A and pose B, which completely strips away any organic acceleration. I want to reassure you right now, the problem isn't your lighting, and it definitely isn't your frame rate. The trap you're falling into is letting the software do the heavy lifting for you. When you just set a start keyframe and an end keyframe, the software defaults to this linear interpolation to fill the gap. And sure, it creates motion, but it actively destroys life.
We really need a complete mindset shift here. Computers think in straight lines, but living beings, we move in organic curves. The fundamental mistake that beginner and honestly even advanced animators make is relying on that mathematical point-to-point keyframing. But real life simply doesn't happen on a straight diagonal line. Real living beings accelerate as they start moving and decelerate as they stop. To fix your animation, you have to transition your mindset away from straight mathematical lines and start using custom Bezier curves and continuous flowing S-curves. You have to be the one to dictate the timing and the path, replicating the organic, sometimes totally messy way that biological creatures actually move through physical space.
Let's look at exactly what those organic curves look like in practice. Take a single, simple action, like an arc-based head turn from Ava. Step 1 is anticipation, also known in the biz as the dip. Notice how, instead of her head just rotating directly from left to right like a literal machine, Ava's nose actually dips downward first into an arc before sweeping up into step 3, the final position. That continuous flow in step 2, that is what sells the entire movement. It's like a giant puzzle coming together. Dead 3D animation moves point to point. A live animation moves in these continuous flowing curves. It proves a massive point for us. Just making a model move is absolutely not the same thing as making a character act.
All right, moving on to our next major concept, overlapping action and drag, the physics of life.
Nothing in nature comes to a complete halt all at once. Think about it in the real world. When a human body is running and comes to a sudden stop, momentum dictates that everything keeps pushing forward based on weight and inertia. In stiff 3D animation, everything keyframes together. The hip stop, the head stops, the close stop, all on the exact same frame. The result? The character looks like a solid chunk of unmoving plastic. To breathe life into your models, you have to respect physics and separate out your stopping times. Now, what's really interesting about this slide is how we can map out this exact sequence of physics mathematically. Look at this breakdown when Ava abruptly stops her run. Her primary body stops right at frame 10. But the motion doesn't end there. Her oversized hoodie and her hair strands continue moving forward, settling sequentially on frames 12 to 14. That is the weight settling. Finally, the straps on our tech goggles, the lightest, most flexible elements, exhibit the ultimate drag, finally settling all the way over on frame 16. This sequential offset is the exact opposite of that stiff plastic stop where every single element freezes together.
2 to 4 frames. That is the magic window. In Ava Thompson's animation pipeline, secondary elements are offset by just this tiny fraction of a second. I mean, it seems so small, right? Literally shorter than a blink. But offsetting your secondary elements by this exact margin is the absolute crucial secret that tricks the human brain. Your brain processes that micro delay and immediately perceives actual physical mass and inertia. It tells the viewer, hey, this object has real weight and it exists in a world with real gravity. It is a tiny, tiny technical adjustment in your timeline that yields massive artistic results. Now let's tackle microexpressions and asymmetry. When you're building a facial rig, it is so incredibly tempting to just let the computer perfectly mirror the left side over to the right side. I get it, it saves a ton of time. But perfect symmetry creates a deeply unsettling, lifeless look. Honestly, it's a fast track straight into the uncanny valley. True human expression is inherently asymmetrical. Whether we're happy, sad, or just casually talking, our facial muscles fire unevenly. And this brilliantly illustrates exactly where the human soul lives in animation, in the imperfections. Symmetrical faces look completely artificial, but an asymmetric smile, where just one single cheek is pulled slightly higher, looks genuine. Think about staggered eye blinks. Ava's eye blinks don't even happen simultaneously. One eyelid leads the other by a fraction of a frame. Even subtly uneven eyelids, with one resting slightly lower, add immense depth to the character. Ava's animators intentionally break facial symmetry on almost every single key pose. They're actively scrubbing away that artificial 3D software polish and replacing it with genuine human soul. So the crucial point is synthesized perfectly into this fundamental truth. Your 3D animation feels dead because you are animating objects instead of performances. It is not about lacking technical skill, and it's certainly not about needing a more expensive software package. It's a fundamental philosophy. You literally have to stop treating your models like rigid action figures that you just pose from point A to point B. You have to bring together all these technical details we've covered today, embrace those organic arcs, delay your secondary motion to show true weight, and deliberately break symmetry in the face. You aren't just moving polygons, you are directing an actor. Which leaves us with this final, provocative question to consider. Next time you open Blender, Maya, or Unreal Engine, are you letting the computer do the animating for you? The software naturally wants to make things linear, it wants to make things symmetrical, and it wants everything to happen simultaneously. It wants to just do the math. But math doesn't have a soul. Study the arcs, respect the physics of overlapping action, and embrace the messy, beautiful asymmetry of human expression. Stop relying on those software defaults. Take back control of your keyframes and start breathing actual life into your 3D models. Thank you so much for joining me for this explainer, and I will see you next time.